So this one is entitled Conceptual Study of Cross-Linked Radio Occultation of Venus Atmosphere, CROVA, using multiple small spacecraft. And our presenter is Hiroki Ando.
Thank you, Chairman. I am Hiroki Ando and a member of radio occultation in Akatsuki mission. Today, I would like to talk about our conceptual study of cross-link radio occultation of Venus atmosphere using multiple small spacecraft. Understanding planetary atmospheric circulation is fundamental to understand the diversity of planetary environments. In the case of Venus, a super rotation is very important, as you know. And atmospheric waves are essential to understanding atmospheric circulation because the waves transport momentum and heat and determine atmospheric motion and thermal structure. Recently, a lot of exoplanets, such as Jupiter's and super-Earths, have been found by space telescope measurement. And some 3D modeling studies, such as Schumann and Pogani and Schumann et al., suggest that the equatorial super-rotation occurs on exoplanets and is attributed to the angular momentum transport due to the interaction between equatorial Kelvin waves and mid-latitude Rossby waves. Let me get back to the talking about Venus. As I mentioned yesterday, angular momentum transport associated with thermal tides is one of the most likely mechanisms how to produce and maintain the Venusian atmospheric super-rotation. And recently, Takagi et al. 2022 suggests that the Venus atmospheric super-rotation is attributed to the angular momentum transport due to the interaction between equatorial Kelvin waves and mid-latitude Rossby waves. So this implies that the mechanisms of the Venusian and exoplanetary atmospheric super-rotation are partly common to each other. It is very hard work for us to visit exoplanet, but it is much easier to go to the Venus. So I think Venus is one of the best samples to investigate the atmospheric super-rotation on exoplanet. However, we cannot examine the variety of the modeling studies about Venusian atmospheric super-rotation because we do not have sufficient information about the three-dimensional structures of waves and disturbances. Recently, some observational studies clarify the horizontal structures of Venus atmospheric waves. For example, Dr. Koyama and Dr. Imai clarified the horizontal structures of thermal tides and Rossby waves at the cloud top altitude. But the thick cloud prevents us from investigating those in and below the cloud layer. And the vertical structures of atmospheric waves can't be investigated by optical measurements. So it is difficult for us to investigate three-dimensional structure of the atmospheric waves. One of the methods to investigate the vertical structure of wave is radio occultation technique. As I mentioned yesterday, from radio occultation data, we can retrieve vertical profiles of temperature and pressure very precisely. In addition, we can also retrieve vertical profile of H2SO4 vapor mixing ratio. This slide shows an example of vertical profiles of temperature and H2SO4 gas mixing ratio obtained by radio occultation. As shown in the left panel, we can retrieve high-resolution vertical temperature and pressure profiles down to 40 kilometer altitude, which is well below the cloud layer. In addition, mixing ratio of H2SO4 gas, which is one of the main cloud materials, can be also retrieved. And by using traditional radio localization technique, some atmospheric waves in the specific latitude region have been clarified. Left figure shows Rossby waves in the polar region, and right figure shows the thermal tides in low latitudes. But global and three-dimensional structures of atmospheric waves and disturbances have not been clarified. In addition, daily variation of atmospheric structures can't be also investigated. And this is because observational region and chance are limited by orbit and geometry of spacecraft. So how can we solve the problems in the traditional radio localization method? One solution is to put a receive antenna near the planet, and then all the problems in traditional radio localization could be solved. And then we are considering now cross-link radio occultation of Venus atmosphere. And we name this mission plan CLOVER. So please let me use the term CLOVER hereafter. Cross-link radio occultation measurements have been already conducted in the Earth's atmosphere. By using cross-link radio occultation using multiple GPS satellites, vertical pressure and temperature distributions at various longitude, latitude, and local times can be obtained in a short period. Please look at this animation. Horizontal axis is longitude, vertical axis is altitude. And this animation shows a diurnal variation of temperature anomaly in low latitude. Therefore, this temperature anomaly is associated with equatorial Kelvin waves. And from this animation, we can clarify the three-dimensional structure of equatorial Kelvin waves and its three-dimensional propagation characteristics. And we expect that this technique can be applied to the Venus atmospheric measurement. Engineering members in the University of Tokyo, Nakasuka and Funase Laboratory have developed and launched small satellite which orbit the Earth. And based on this experience and performance, they are now planning to conduct the planetary exploration by using small satellites. And they also find the solution in which cross-link radio occultation measurements can be conducted under the realistic condition. This slide shows a spacecraft design in CLOVER. At the present stage, CLOVER is considered to be composed of one main orbiter and two sub-satellites. And orbit inclination and periapsis, apopsis altitudes, orbit period, and size, mass, and delta V are as follows. And the designs of main orbiter and some satellite in CLOVER are based on Procyon and Eclipse, respectively. This slide shows an example of orbit and data distribution. And for Earth days, this period is equal to the rotation period of super rotation at the cloud-top level. We will obtain about 180 data points as shown in this panel. And if we conducted CLOVER for 30 Earth days, we will be able to get more than 1,000 vertical profiles of pressure and temperature globally. This implies that if a CLOVER enables us to acquire four-dimensional meteorological data in the Venus atmosphere. And we are now considering what CLOVER brings us. One is a three-dimensional variation of the atmospheric structure below the cloud layer. Nobody has not investigated and observed it. So this makes this mission heuristic. And we can also investigate three-dimensional structure of waves and disturbances. And then we can also retrieve global distributions of H2SO4 gas mixing ratio. And by using two wavelengths, we might be able to retrieve global distributions of H2O and SO2 mixing ratios. These results are very useful for us to investigate the Venusian cloud physics. In addition, we can also investigate global distributions of electron density in the Venus ionosphere and gravity field in the solid body. And we are also now considering how we can collaborate with new Venus missions. CLOVER is specialized in investigating the atmospheric dynamics because we can clarify three-dimensional structures of waves and disturbances. In addition, atmospheric circulation can be speculated because waves transport angular momentum and very related to atmospheric circulation, such as mean measure circulation and zonal wind distribution. And main purpose in the new Venus missions conducted by NASA and ESA is to investigate the surface and distribution of minor gases. So if CLOVER was conducted at the same timing as these new Venus missions, we would be able to investigate the Venusian atmosphere from various perspectives: dynamics, chemistry, and cloud physics. This is summary. I talked about our mission concept of CLOVER, which might enable us to acquire four-dimensional Venusian meteorological data. And we have finished the conceptual design and now discussing the mission plan in more detail in terms of both science and engineering, not qualitatively, but quantitatively. And we should also consider how CLOVER can collaborate with new Venus missions. The scientific results obtained this collaboration will enable us to investigate the Venusian atmospheric sciences from various perspectives. In addition, this will lead to the understanding of exoplanetary atmospheres. And I would like to emphasize that a cross-link radio-localization technique can be applied to other planetary atmospheres, such as Mars, Jupiter, Saturn, and Titan, and so on. And cross-link radio-occultation might make it possible for us to acquire these four-dimensional meteorological data. That's all. Thank you for your attention.